Oh man, lost my place. Let me go back to that slide. Oh, way too far. Where did I want? Ah, right there. Okay, so let me go ahead and get back to our discussion on development length. So here's our expression that we've been dealing with. I know it seems nasty, but in the end, I think it's a fairly straightforward plug and chug expression. The big thing with development length is ensuring that you know where you're getting the values that are plugged into it. I mean, if you know what psi value to use and what CB value to use, this is about as simple as it gets. Okay, so here's our plug and chug expression. Our really new factors are the psi terms, CB, and then KTR, our transverse reinforcement index. So the psi value, psi t, is our top bar factor. Essentially, if you've got top bars, quote unquote, your psi value is 1.3. Otherwise, you've got a psi value of 1. Your epoxy coating factor, if you're dealing with uncoated bars, it's always going to be 1. If you're dealing with epoxy coated bars, it's going to be larger than 1. It just depends on your cover and your spacing. If you've got really narrow spacing, it gets bumped up quite a bit. Again, epoxy coated bars are slicker. They don't bond as well, so you need more development length in order to grip those bars and develop the full capacity. Bar size factor, if you achieve the same area of reinforcement with a bunch of really small bars as opposed to a few really big bars, you have more surface area. More surface area means more room to grip. More room to grip means you get a benefit on your development length. So you actually reduce your development length 20%. So smaller bars, we use a psi value of 0.8. Otherwise, we use a psi value of 1. So that's your bar size factor. Okay. Spacing and cover requirements. CB, remember CB is trying to reflect that cylindrical core distance, that sort of cylindrical cracking surface that you get from bond failures. It's either from the center of the bar to the edge or the center of the bar next over to the next one, or half the distance to the adjacent bar. Your transverse reinforcement index, again, plug and chug. You take the area of transverse reinforcement, which is basically the area of your shear stirrups. You take the center to center spacing of the transverse reinforcement, which is just your stirrup spacing, and then in your largest number of tension bars in a single layer, so that'd be an N of 3, and just take those values, plug and chug to get a KTR, as you see here, and KTR is measured in inches. So, all right, sound good? All right, couple notes. That product that you see above, regardless of what you look up or what you calculate, it's got to be taken less than or equal to 1.7. So if you get a value larger than that, just cap it down. Also, if you recall, remember how you can reduce a development length based on the difference between the area of steel you actually need for design and how much you actually provide it. So, for instance, if you're doing a beam design and you do all the calcs and you get to, what was it, like step 8, and you get that the area of steel required is 5.72 square inches. And then you decide to use 6 number 9. So you used more steel than was needed. You can take the ratio of those two and drop your development length down a little bit. So the 5.72 over 6 in that category, or in that example. All right, sound good? All right, so we've got this example, and I think we did some of it, where we looked at KTR equals 0, and I don't think we did the computed KTR. And we calculated the development length of this beam, and I think we saw that this is pretty simple. It's pretty plug and chug. All right, so let's go through this, and the KTR one's going to be, it's going to be real quick. So, okay, you all have the beam in front of you, right? Okay. Okay, so let me walk through 15A really quickly. So here was our adjustment factors. All the psi values were 1 because we were dealing with bottom bars that were uncoated and that were number 8, so they were bigger than number 6s. In this instance, we dealt with a KTR of 0. So that term on the denominator ended up being 1.5, which was good because that was less than 2.5. Excuse me. Plug and chug, and your development length's 54.8 inches. I mean, that's about as simple as it can get. Now, all right, everybody okay with this? Okay. Okay, so now what I want to do is I want to see, well, how does that value change if I actually compute KTR? Let's see what happens. So, okay, so let's compute KTR. So we're going to need the area of transverse reinforcement, we're going to need the spacing, and the number of bars in a single layer. So let's take this one at a time. Help me out. What is the area of transverse reinforcement going to be? Remember, that's the area of your shear stirrups, which that might be a little small, so let me blow it up for you. So what's the area of your shear stirrups going to be? Oh, whoops. Did I skip ahead? Oh, there we go. All right. Oh, actually, I don't think it matters. It's the same one. What's the area of the transverse reinforcement going to be? All right. Help me out with this. What size are the shear stirrups? Number 3s. Is it 1 bar or 2 bars? 2 bars, because it's a U-shaped stirrup. So what's the area of 2 number 3s going to be? What's that? No. No. That's would be the length. The area. Hold on. You all have this, right? Yeah, 0.22. I mean, you all have this, right? I mean, the area of multiple bars. I mean, you all have that handout, right? I mean, what's the area of 2 number 3 bars? It's 0.22, right? Remember, this is a number 3 U-shaped stirrup. 0.22 was a pretty common value that we use in our shear design calcs, right? Because essentially what we're calculating is AV. That's what AV is. So that's 2 number 3 bars. Okay, what's the stirrup spacing? 8 inches, right? And what's in? How many longitudinal bars are in a single layer? Number of bars going like that. How many bars do we have? Should be 3, right? There's 3 bars. You see what I mean? On that example, what is it? What? Yeah, how many would be? 4, right? Makes sense. On example B, it'd be 4, right? Everybody see that? Okay, so N is 3. So our KTR is 40 ATR over S times N, which is 40 times 0.22 inches squared. And then S is 8 inches, and then 3. So KTR is 0.367. All right. So because of that, we can go through and we can compute that ratio, that CB plus KTR over DB, which is CB. And what is CB? I think y'all go back to your original notes. There we go. Plus KTR, which we just did, 0.367. So last time we just ignored that. We just said, well, KTR is 0. And then DB, what is DB? 1. So plug and chug, and that's going to give you 1.867. Is that an acceptable value for use? Why? It's below 2.5. That's good. Remember? Hold on. Yeah. I see what you're saying. You were thinking of that. Yeah. Now remember, this ratio is limited to 2.5. Okay. Sound good? All right. So we can now go through and compute our development length. And it's pretty simple. All right. Three over 40 Fy lambda FC prime psi t psi e psi s. We got that ratio. Oh. And then dB. Okay. So again, what I'm going to do is I'm just going to do a single fraction, everything up top and everything on the bottom. So on the top, we've got 3 times Fy. What's Fy? 60,000. Exactly. We use PSI, right? Because our FC prime, we're taking the square root. We put in PSI there, we get PSI out. So we've got to make sure consistent units are used. So 60,000 PSI. And then what were all of our psi values for this problem? 1. They were all 1s. And then our bar diameter, which is 1 inch, right? We're dealing with number 8s. So 40 times what's lambda? 1. And then we have the square root of, is this 3 or 4? 3,000. Remember, you plug in PSI, you get out PSI, and then our ratio 1.867. $44 even? That's what I got. 44.0 inches. So before, what did we get? We got like 58 something, right? So that distance has been cut significantly just by that little number right there, okay? I mean, you think you cut a foot off of embedment of that bar just by throwing that number into the calc. It's definitely worth mentioning. All right, make sense? Okay. Anybody have any questions? Okay, all right. Go to our next one. Okay, all right. So example 15b. Okay, so let me pull this up. All right. So same deal, we're going to say, all right, what if we ignore KTR, what if we actually compute it? But the beam we're looking at is a little different. So a couple things. Number one, we're dealing with 3.5 KSI concrete, and I decided to mix it up a little bit. We're going to use lightweight concrete for this. So our lambda is not just 1, it's 0.75. We're still dealing with 60 KSI steel, but then look at this point right here. Design yielded a required area of steel of 2.88. So we needed 2.88 square inches of steel for this design. But what did we go with? When the design was carried out, we used 4 number 8s. So obviously there's more steel in the beam than is needed, right? Because of that, we can take whatever development length we compute and cut it down by taking this divided by that. Make sense? So maybe we only need to use, I don't know, 95% or 90%, whatever the ratio of those two numbers are. That's what we have to use for the purposes of design. Make sense? Okay, all right. Okay, so let's write a couple things down. All right, so get that out of the way. All right, so we have an FC prime. In this case, it's 3.5 KSI. We've got a lambda of 0.75. We've got Fy of 60. And we've got, in this case, we have an area required of 2.88. So again, remember you do the design, you get to like step 8, and it says the required area of steel is 2.88. That's where that number comes from. All right. What's our bar diameter? It's a number 8. So what's our bar diameter? 1. So we got that from the fact that we were dealing with number 8 bars. Okay. All right. So let's keep this simple. Let's start off and go through our factors one at a time. So I got 4 of them I'm going to do right off the bat. I've got psi t, psi e, psi s, then that's CB. Let's take this one at a time. All right. Psi t, what's psi t going to be? $1.3, right? It's not 1, right? Because we've got more than 12 inches of concrete under here. It's like 23 inches. And again, psi t is a top bar factor. It's 4 bars on the top, okay? So psi sub t is going to be 1.3 in this case. So I'm going to say on the example 1.3. And then for posterity, for your notes, I'm going to put top bars. So that way I indicate a value and then I put a value and I indicate why it's there. Okay, psi sub e. What's psi sub e going to be? 1. We're still dealing with uncoded bars. That's, yeah. Okay, all right. Psi sub s, our bar size factor. 1 as well. Because it's bigger than number 6's. Okay, now C sub B. All right, let's walk through that. Remember, that's that cover distance. All right. So let's see what we get. How far is it? And remember, there's 3 options, right? How far is it from here to this edge? 3. How far is it from here to this edge? 3 inches. How far is it from here halfway over to the next bar? 2 inches. Which one do we use? 2 inches. Make sense? Simple stuff, right? Okay. Now, before we do anything, I might as well just go ahead and put here on the side, I'll put note. Go ahead and calculate those two. Remember, it's not C. It's supposed to be an E. That has to be less than or equal to 1.7. You go through and calculate it, and what's it going to be? 1.3. So that's good. Okay, all right. That one's simple. So we're going to do one with KTR equals 0. All right? So if KTR equals 0, what do? We say, all right, C sub B plus KTR over dB is what? It's 2 inches plus 0 inches divided by 1 inch, which is 2. Is that an acceptable answer? Yes, because that value has to be less than or equal to 2.5. All right. So, therefore, our LD is going to be, let's see, we've got 3 over 40. We've got Fy over lambda Fc prime, square root of Fc prime, and then psi t, psi e, psi s over that ratio. Then dB. Then just to keep this simple, I'll plug and chug on a single expression. So 3 times Fy, and what's Fy? 60,000. All right. Psi sub t, psi sub e, and psi sub s is 1.3, 1, and 1. And we're dealing with number 8 bars, so 1 inch. All right. 40 times lambda, what's lambda? There we go. Times the square root of 3,500. Again, you put in PSI, you get out PSI. And then the ratio of 2. What does that give us? Say it again. 65.9. Yes. All right, so 65.9 inches. All right. Now, can we do anything with that value? We can reduce it. All right. So we can say LD reduced we can say we take that 65.9 inches and we multiply it by a ratio. We take the area of steel that we needed divided by the area of steel we actually have. How much did we need? 2.88. And how much did we actually provide? 3.14. Excuse me. So what does that give us? Not too bad, right? Now again, you can get some benefits with these little effects like reducing it, KTR. Now, some of you who might be thinking a little more practically might still be going, well, gosh, that's pretty big though, right? We have to embed that bar 5 feet before we can develop its capacity. And yeah, so there are some ways we can get around that, which we're going to talk about after this. But I just wanted to make that point that, yeah, these are some pretty big values. There are ways we can get around that. All right, everybody good? All right, any questions? Yes, it can. But as you'll see here in a minute, we go through and do that, we're going to get 53.2 inches at the very least. You'll see how that works, though. All right, so let's go through and do KTR. Let's see what time it is. We're making good time. All right, so okay. We'll say KTR does not equal 0. Let's see what we get. So to do KTR, we're going to need an area of transverse reinforcement. We're going to need a stirrup spacing, and we're going to need a number of bars in a single layer. So help me out. What is the area of transverse reinforcement for this beam going to be? Say it again. Stirrup spacing, what is it? It's 4 inches? 8 inches. How many bars are in a single layer? 4. All right. So KTR is 40 ATR over S times N, 40 times um, 8. And then plug and chug, that gives you, what does that give you? 0.275. All right. In the interest of expediting what comes next, because it literally is plug and chug. Let me just sort of summarize a couple values. So we've got KTR. We could compute CB plus KTR over D. And if you do that, you're going to get 2.275. Is that an acceptable value? Yeah, because it's less than or equal to 2.5. All right. If you compute LD, and are you okay with me just sort of telling you what the answer is? Because it's plug and chug. All right. You should get 58.0 inches. And if you then further reduce it, you'll get 53.2 inches. Oh. All right. Any questions? Yes.
A little bit longer of a development, use a little bit less area to steel.
No. Are you talking about like in beam design mode, if I allow for more development, can I use less area? No. Because what you're determining is how far that bar needs to be embedded to develop its full capacity. Here's the idea. If I have a bar embedded into this wall, let's say it's only embedded 1/4 of an inch. I'm going to be able to yank it right out. Okay? Embedded 53.2 inches, it gets to the point where once I get to 53.2 inches, I can embed it 5,000 inches and it wouldn't matter. All that's ensuring is that I have actually developed its full capacity. That doesn't mean I get more capacity by putting it in further. Because the idea is if I start yanking on it, I stop being controlled by the bond strength between the steel and the concrete, and my strength is just Fy times the area. In order to get more strength at that point, I would just need more area. So, does that make sense?
Now that's almost further up as later on. Okay, that's where it's just straight in. Can't you take it down and get more strength out of it? Or get more
You have a knack for asking questions I'm going to talk about in the next 20 seconds. Here, hold on. You're going to laugh. All right. Oh. Okay, it's literally the next slide. Literally the next slide. But you are raising a very good point. That is, these development links, they're long, you know. Is there a way of reducing it to some effective means? I mean, you know, you look at some of these values, you say, well, if I had a beam framing into a column, you're saying that column needs to be 6 feet wide just to develop the beam? No. You can get around that with some other means, and that's where hooks come into play. Now, it's not as simple as just take a piece of bar and bend it. There are actually some standard details that we use for hooks. You know, how long this leg needs to be, what bend radius that needs to be, and what have you. But we deal with 2 types of hooks in the world of reinforcement: a 90-degree hook and a 180-degree hook. And here you can see the kind of difference between the two. what we find is that development length can be substantially reduced if you account for the concept of, or if you account for using a hook. Now there are a couple of things that, that help you out. Number one, hooks are a lot easier to compute in terms of their development length because there's no top bar or bottom bar location factor, and there's no reinforcement size factor. It stops mattering because you're not relying on the concrete to grip the bar in the same fashion. Before, it was literally like the tug-of-war concept. Here's the rope, here I'm grabbing onto it. The function of, or how strong I am in that tug-of-war competition is, I mean, yeah, it's a function of how strong I am, but really it's governed by that grip I have. If I have a really weak grip, I'm going to lose regardless how strong I am. Okay? Here, it's a different story. Here, instead of gripping, I guess, the rope in the tug-of-war scenario, instead of gripping the rope like this, it's almost like I have it looped into my arm. Okay? It stops becoming a function of how strong my my grip is between my hands and the rope. It's just holding it like that. So I have a little bit of an advantage in that regard. What you'll find is that if you compute the development length of hooks versus straight bars, hooks have significantly less development length because you don't need as much length. They're gripping the concrete in a different and arguably better fashion. Okay? Now the expression is pretty simple. It's only a function of your epoxy factor because you can still get that slippage effect from that slick bar. A couple things, a couple other things. So these are just some provisions to make your life a little easier for hooks. These are a couple of reductions. So if you've got a 90-degree hook, in other words, if I'm talking about that one up above, if you've got a 90-degree hook, if you've got substantial cover on that hook, in other words, I think I have an image right here. If you've got substantial cover on either sides and behind the hook, you're allowed to take whatever you calculate and multiply it by 0.7. Basically, it's if your side cover is greater than 2.5 inches, and if your cover on the back is greater than 2 inches, you can multiply that by 0.7. Also, if you've got a really tight stirrup spacing, you can take that development length and reduce it even further. So these are cumulative. If you meet both of those, you multiply by 0.7 and by 0.8. Okay? This is just an image trying to explain that stirrup spacing requirement. So if your stirrup spacing is less than or equal to 3 bar diameters, which is this, or if that last one is less than, and if that last one is less than 2 times the bar diameter, you can reduce it even further. Lastly, you can do that. You can do the same thing where you can reduce the development length based on the area provided versus what you actually needed for design. Does that make sense? So to go back to what you were saying, yeah, you can cut that down quite a bit by using a hook, okay? And that's it's just a different expression because there are different parameters that affect the behavior of a hook versus a straight bar. Sound good? All right, it is 10:44 right now, and I don't think we're going to have time to get into this. But what we're going to do for this problem is we're going to compute the development length of this problem in 2 different fashions. We're going to look at almost the worst case scenario, a straight bar with KTR equals 0. Then we're going to consider a bar ending in a 90-degree hook, and we're going to try and reduce it as much as we as much as we can. Now what we're going to find is, and I'll just go ahead and tell you this, when you look at a straight bar, you have a development length of 68.4 inches, and we'll see how we get to that. But for hooks, we're going to find 32.1 inches. So we're going to be able to cut it almost over in half simply by using a hook. All right, so that's just sort of food for thought for later. All right, make sense? All right, that's all I have for you all today. I'll see you all on Wednesday. Okay, now I'm fairly certain that your development length homework actually doesn't have any hooks in it, although I don't think it really mattered if it did. It's just another plug and chug. But we'll close this out real quick on Monday after the exam and then get into our final big topic of the semester, which is columns. All right, That's all I got for you all. I will see you all on Wednesday.